Hello, dear students. I'm Professor Isha Galgalikar, and we are going to discuss today boundary layer theory. Let me first introduce regarding boundary layer theory. The concept of boundary layer was first introduced by L. Prandtl in 1904. This theory relates to the flow of fluid when it comes into contact with any boundary, whether it is the pipe boundary or whether it is any plate which has been inserted into the flow. When a real fluid, that is, when a viscous fluid flows past a stationary solid boundary, a layer of fluid that comes in contact with boundary adheres to it. That is, if a flat plate is inserted into the flow, then generally it would retard the flow near the boundaries. And wherever we see this effect, that is up to the depth we see this effect, we apply this boundary layer theory. For all other places where this effect is not seen, the potential flow theory is applied. Hence, retardation takes place near the boundary. Even the adjacent layers are retarded. So if a boundary, or if let us say a flat plate is there, let us say a fluid is flowing like this in this manner, and suddenly it comes into contact with a flat plate, then obviously the flow diversion will take place. With this, there will be some retardation seen in the velocity near the flat plate. So in this zone, some retardation in velocity is seen, and this theory specifically applies to this region. So a small region in the intermediate vicinity of the boundary is developed in which the velocity of flowing fluid increases rapidly from zero at the boundary surface and approaches the velocity of the mainstream. That is, exactly near the boundary surface, the velocity becomes zero, while it, as I go up, that is on this side, the velocity slowly and steadily increases, and then at certain height it becomes same as that of the mainstream velocity. So this is the mainstream velocity here, and here also initially it is zero near the boundary and then it increases with the depth. Here the fluid exerts shear stress on the boundary, and the boundary exerts an equal and opposite force on the fluid, which is called as the shear resistance. Let us see certain boundary layer characteristics. So here you can see in this specifically the snap which is provided. So here you can see this is the mainstream velocity. These points you can see this is the mainstream velocity, and this is the flat plate, blue colored plate, which is inserted here. So there is retardation in it. Now, while looking to this plate, certain terms we must know, that is, the edge facing the direction of the flow is called as the leading edge. So you can see it is the leading edge, while the edge that is at the end of the plate is called as the trailing edge. Near the leading edge, the boundary layer is wholly laminar and velocity distribution is parabolic. That is, though this flow is turbulent, then also here retardation takes place near this zone or near this plate, and hence here the flow is completely laminar, or we can say the boundary layer is laminar. That is this zone. The velocity distribution is parabolic and the boundary layer is laminar. Then again the depth also increases, while this is the transition zone. Again we know according to the Reynolds number the flow is classified into three types: laminar, transition and turbulent flow. Similarly, boundary layers are also of three types: laminar, transition and turbulent boundary layer. So initially it is a laminar boundary layer. So velocity, we may say that Reynolds number, sorry, not velocity, Reynolds number, we may say that it resembles the laminar flow. Then we have the turbulent boundary layer here. So at the trailing edge, normally we have turbulent boundary layer. At the leading edge, we have the laminar boundary layer. For turbulent boundary layer, the roughness projections are covered by a very thin layer which remains laminar, called as laminar sublayer. You can see even in the turbulent boundary layer, we have one layer which is laminar and which covers all the roughness projections. So here on the plate I may have certain roughness projections, and these are covered by this layer which is also called as the laminar sub layer. So this is about certain characteristics of the boundary layer. Now we will see certain definitions related to it. So first is boundary layer thickness. So how much thick is this boundary layer, and up to what thickness does this theory apply to it? So we can see here the definition says the distance from boundary in which velocity reaches 99% of the velocity of the free stream. So in this figure also I can show you that here the mainstream velocity is denoted by capital U. So here I have everywhere capital U. Near boundary it is 0. We have already seen. Slowly it increases. So you can see this is the velocity profile. So it goes on increasing. So initially this is 0. Then at this point the velocity has increased. Again it is increased. Again it is increased. One point comes where the velocity is 99% of the mainstream velocity. That is small u is equal to 0.99 capital U, and this depth is called as the boundary layer thickness. So it is measured because it is a thickness, its unit of measurement would be meters, and that thickness where the velocity reaches 99% of the mainstream velocity is called as the boundary layer thickness. So we have to remember this. It is denoted by delta. So you can see here also delta is there, and here also delta is there. So it is denoted by delta. So this is the boundary layer thickness. Then second definition related to this is displacement thickness, momentum thickness, and energy thickness. So what is displacement thickness, momentum thickness, and energy thickness? Displacement thickness is defined as it is the distance measured perpendicular to the boundary by which the main or free stream is displaced on account of formation of boundary layer. So we may say that displacement thickness, it is actually thickness, it is distance measured perpendicular to the boundary. So if this is the boundary, then it is measured perpendicular to this is the perpendicular distance by which the main free stream is displaced on account of formation of boundary layer. So when my main stream is flowing, it is going to be displaced by certain distance, and that distance measurement is called as the displacement thickness. It is denoted by delta asterisk. Its formula is also given to us. This is denoted by delta asterisk, and this theory, as it is applicable in only boundary layer thickness, hence its limits are from 0 to delta. It is given by integration of 0 to delta 1 minus small u upon capital U dy, where small u is the velocity in the boundary layer thickness and capital U is the mainstream or free stream velocity. Small u is generally taken as 0.99 capital U, 0.99 into capital U. Just a minute. It is denoted as 0.99 into capital U. Sorry for interruption. Similarly, we have the momentum thickness. So momentum thickness, like the velocity reduces, so momentum also reduces because of the disruption that we have, that is a boundary layer or flat plate we have within the flow. So momentum also decreases, and this momentum thickness, there is loss in momentum thickness basically. So it is defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for reduction in momentum of flowing fluid on account of boundary layer formation. Or simply it can be said that, if I have a very thin plate, or very thin, you can say, flow zone from which the flow takes place, I'll have some momentum of it. This momentum, that is very small momentum, and whatever loss of momentum is taking place in the boundary layer zone, that should be same. So that is called as a momentum thickness. Whatever thickness is there, I may have certain mm, 5 mm, 10 mm, whatever thickness is there, that momentum and the momentum loss in the boundary layer should be same. That is called as the momentum thickness. So we have to find out that thickness. It is denoted by theta, and again its zone is from 0 to delta. It is given by u upon capital U, 1 minus small u upon capital U dy. Similarly, we have energy thickness. So you may now have understood from the momentum thickness also what could be the energy thickness. There is kinetic energy loss while the flow takes place, velocity reduces. So again, energy thickness is that thickness, small thickness which would compensate for the loss in the energy in the boundary layer zone. So again, it is given by delta E. It's again, the limits are from 0 to delta, given by u upon capital U, 1 minus u square upon capital U square dy. So this is called as the energy thickness. These are the certain definitions, or we may say the basic terms related to energy thickness, displacement thickness, momentum thickness, and boundary layer theory. From this, if any function is given to us for velocity, that is capital U, we can find out what is the function for momentum thickness, energy thickness, and displacement thickness. And if the values of delta, that is boundary layer, is given to us, then we can calculate the values of energy thickness, momentum thickness, and displacement thickness. Other things we will see in the next class. Thank you very much for listening.